Thank you for the 20 of you that came. I don't know. All right, so this is the lecture on conceptual modeling. Actually, I don't think it's going to take the full 2 hours. So I think we'll do a general, maybe like any tricky topics that we want to talk about. But I also wanted to do, I had this idea and I wrote it really quickly this morning to do a recap of some of the token stuff with a worked through simplified demo that might make the concept a bit more straightforward, because actually it was something that I struggled with for a long time. And I was talking, I don't know if you're here, but I was talking to 2 students after the lecture on Tuesday, and I kind of described something, and I think it clicked in the 2 students. Are you here, if you know what I'm talking about? Maybe not. Was it you? You 2. About the adding up the numbers? Yeah. So I've got a demo that we can actually work through that should really make hashing simple and the token idea simple. So we'll start with that, then we'll do the conceptual modeling, and then we'll do general stuff if we have time. Does that sound really good? All right, so let's build a very first principles simplified version of something like a JWT, a JavaScript web token or some sort of token with some hashing to really show through and talk through what's going on. And I got to just caveat, I wrote it very quickly so that maybe there's some slide issues and things, so bear with me on that. Yeah, come in. Just pull the door shut, please, when you finish up. So let's build a token together from first principles on the whiteboard. Does that sound really good? All right. So the first thing we need to do something like this is design a toy hash function. So obviously what we're describing here is a hashing algorithm that is utterly useless, but does the general purpose of hashing in a way that we can actually keep track of mentally. So, clearing out my pockets. Do you want me to do it on the whiteboard or on a note document or something? What's easier? Better for you. For you guys? You can probably see it. Yeah, okay. Yeah, good point. All right, let's do it. Let's do it here. Yeah, I could do that actually. I haven't used this in ages. Open. Yeah, I used to use it all the time. You can see here. All right, just give me a blank whiteboard. Okay, let's go back to here first. All right, so first let's design a simple hashing algorithm. So hashing is a way to convert an input string into a reproducible value. That's one way, unidirectional. So let's hash some small strings really simply. So the first thing we need to do is design a way to convert a character or the thing that we're hashing to a numerical representation, because hashes are numerical functions. And let's just be really simple and say A is 0, B is 1, C is 2, right? So not quite ASCII, but ASCII-esque in the sense that we're starting A at 0. A is 1, sure, yep, thank you. So either would work, right, as long as you're consistent with your toy algorithm. So if we say C is the number 3, A is the number 1, and T is obviously is 20, a really simple hashing algorithm would just be to add those numbers up. And if you think about it, so cat produces the hash 24. So if we think about what makes a hashing algorithm, we described the properties on Tuesday. So you always get the same hash from the same input. Is that true? Yes. If you change the input, you'll get a different hash. That seems true to me. So this does suit the principles of a hashing algorithm in many ways. Now, is this a good hashing algorithm? It's really not. What are some of the reasons why it's not a good hashing algorithm?
Acronyms are going to give the same hash, so
you're going to incur many clashes. Because obviously if I have just D, sorry?
God's going to give the same hash as dog, for example.
That's a great point. In fact, yeah, that's right. So God or TAC will give the same algorithm as the inverse because you're just summing it. But it's still a hashing algorithm. Just happens to be a very efficient hashing algorithm that has many, many clashes. Okay? But it's really simple. We can do it almost in our brains. And if we change something like cat to cap, we get a different hash. Obviously. So we have a toy hashing algorithm. That's pretty cool. Now it's terrible, like I said, but it does have the same properties. So like I was saying, same input gives the same output. A small change, you get a different output. This is really bad because the delta of the change will map to the delta of the hash. Does that make sense? But it's still a small change, gives a different output. And it's still hard to reverse. So if you know this hashing algorithm and I give you the value 24, and I tell you, can you tell me which string caused the hashing algorithm to produce the value 24? You could probably give me all permutations of the strings that caused 24, but actually think about in your minds, how long would that list be? It's pretty long because you could have A 24 times, right? You could have A 23 times and then B in the place of the last A, all the way permutated to cat, to just the letter, is there a 24, how many letters in the alphabet?
26.
So you could have Y or X. So think about that. Even with such a simple hashing algorithm, this should, in your minds, make you click as to how difficult it is to reverse, if you think about something like SHA-256, how difficult it is to reverse from a hash the input string, especially when you consider the complexity of, say, something like SHA-256. It's mathematically actually not possible. Now, it is possible with our toy hashing algorithm. You can actually produce the list of inputs that would create 24. And even then, it would be such a long list that, let's say you're trying to hack my password. It's computationally possible, but it would be really hard for you to find the password with some confidence, right? So that's something that's kind of interesting to do here. And this is actually an analogy for a good strategy to learn something that's really tricky, is to design a toy version of it and do it yourself. And it is one of the best ways to understand very deeply more complex versions. Okay, so we have some toy algorithm to do a hash. Let's sign a token. So remember, a token is this idea of signing a payload being some data that we care about. And in the context that we're talking about in authentication, we're signing maybe something like a user's ID and an authorization level, like the role. So let's say the payload here is the string student. So in this case, we're signing the role of the object. So we assign that numerical value to each of the characters in the word student. So 19, 20, 20, whatever. We add those up. Maybe I won't even need a whiteboard if the slides are. You let me know if you need to work through it together. So we add those up, we get the hash 103. Now that's the hash of the payload. And then we add the secret. Remember, the secret is something that the server knows to decode to verify that the token hasn't been tampered with. So suppose after the login, the server wants to issue a token saying the role is student. Remember, the tokens are generated on the server and sent to the client. The client can then use them back. The secret is only the server knows the secret. So let's say the secret is the string key in this case. We get the secret 41. Does that make sense? We're hashing key, K-E-Y, and we're getting 41. So we do something like 103 plus 41, and then we say mod it. So basically we combine the value that we're tokenizing plus our secret, convert it to a single value, and then we send to the client something like student.47. So when the client makes a subsequent network request, and in the header of that network requests places that token content.hash, or the signature, the server simply back recomputes, because it's got the content, so it gets student. In this case, it's just plain text, so that's fine. So it knows the data. But now, the goal of the server is to make sure, okay, that the client or someone in the middle did not manipulate the content before the signature. Okay, does that make sense? That's the whole goal of this activity. The server needs to trust that this token hasn't been tampered with. So the client is telling the server, hey, I have the role student, and here's my signature for that role. Now, if we've done everything correctly, the server will have all the building blocks in order to recompute the signature in such a way that the signature would only be valid for the payload student. Does that make sense? And the way it does that is recompute the hash for student with the key, and it should get the signature again, which is 47.
Is it kind of like how a checksum?
Okay, a checksum I think is slightly different. So for those who don't know what a checksum is, who's got a credit card or a debit card? This is what you're talking about, right? In their pocket right now? Really? Not? Oh, you use your Apple Pay. Okay, sure. Well, if you've got a physical credit card in your pocket, the last, I think, 4 digits, is it, of your credit card number are a checksum. So they're doing some sort of hashing-like algorithm to the numbers, and all it does is verifies that the credit card numbers are not mistyped. I think maybe it is close enough to a hashing algorithm. Actually, it's probably worth a Google. What are the differences between it? Yeah, it's like it is actually the same idea. Yeah. But I don't know if there's something significant to that makes a checksum different from something like this. But it's probably worth a Google. So you do some sort of computation because the server gets back that student. So it runs student through the hashing algorithm again. It applies the secret, combines it in some way. We just did a modulo. And the result of that should be the signature that is attached to the token. So does this make clear why the secret is a very important component of this whole series? Because without it, well, what's the problem? You guys tell me. Why is the secret important, though? I guess maybe let me put it this way. If we didn't have this idea of a secret, what would the client be able to do? Yeah, they would just recompute the signature. Do you see what I'm saying? It might not be, but sometimes it's just hard for me to understand the intention behind it. Yeah. So because all the client would need to know is which hashing algorithm the server used, and it would be able to regenerate a signature. So there needs to be some secret component applied to the algorithm that you hash in combination with the payload, so that a client can't recompute it even if they know the hashing algorithm. Cool? And so you just simply reapply your two hashing algorithms to your two inputs, the payload and the secret on the server, and you verify that the resulting hash matches the hash that came in the second component of the token. So if someone tampers with the payload, so they make student, for example, admin, this would be a disastrous authorization escalation attack. You would have to, and the client knows the hashing algorithm, which is not that hard. You could probably just try all of them until you get the right one. So you hash the input admin, you get, say, 41. The client doesn't know the secret, so they just leave the signature with what it was. The server receives the payload and the signature, recomputes the hash, and obviously you'll get a mismatch. And so the server can then reject that request. Yeah. And it all hinges on the security of that secret key, of course. So if someone obtains your secret key and knows your hashing algorithm, you're screwed, obviously, because they could just do what you're doing. And quite literally, this is exactly what a token is doing, but with a much more complicated hashing algorithm. So this is really cool now. So if ever you see an authentication token, you might even inspect them in your browser. You can sometimes see them. You'll have in your mind, and you'll know exactly pretty much what was done to generate those and what it means and why we have the period in between it. Because you need to know the payload and the signature of the payload, plus the secret, or whatever sort of other stuff gets sprinkled in. They might do some specific steps or things. I think it's quite, this idea of like cryptography and also like untrusted clients that you're navigating and dealing with who have to do trusted things on your system and how you navigate that all, it's just super interesting that this all works and how it was designed, right? So this idea that like you need to prove to me that who you are in a way that you can't falsify that is very, very interesting. Yeah. Any questions on generating authentication tokens? And the other cool thing here with a token is that you can put any data in the payload. It doesn't have to be an authorization. It could be absolutely anything. So it's like any time you need to provide something to the client and to know that it hasn't been tampered with. Right? You could think of applications outside of web, say, authentication that this is very useful for. Yeah. No questions? Feeling good? Well, that's good, because this is not super simple, so it's good that you understand it. Okay. Cool. Let's talk about conceptual modeling, or a bit of modeling in general. Like I said, I don't know how long this will take, but I'll try and be really clear as to what the value of modeling is. In fact, I think given AI model capabilities in engineering, modeling is going to become even more important, because it's how we describe our systems and our problems, and we get potentially humans and models working together to solve the right and the same problems. So I think it's actually very important. It's been used forever in software engineering. It's not just used in software engineering, it's used in all of engineering, all of science. We model things all the time. You're constantly creating models in your brains of the world, of things that you're studying, of your friends, of your family. We are basically modeling machines, and it's very useful to model things. So let's talk about it. So what is a model in the very broad sense? It's a simplified representation of a complex system. So if it's not simplified, it's not really a model, it's just the system, right? So if you think about trying to do contact tracing in COVID, we modeled, for example, human movement. But of course we have to lose lots of data, because otherwise it's just all human traversal data, for example. And the reason we simplify it is because it helps us reason, understand, communicate it, predict, infer, create linear regressions on some data, right? So we're structuring very complex systems in a way that lets us apply techniques to them. And yeah, models are absolutely everywhere. So a train map, for example, is a great example. So who's been to like obviously we have the metro here and things, but who's taken the subways in London or something? Yeah, so the London Tube network is the most complex underground network in the world, I think, still. Maybe, who's my fact checker today? There's probably some city in China now that will claim a much more complex system, but I'm not sure. I think it is still London. So it's very, very, very complex. It's nothing like the Australian public transport systems, right? It's been built over like 100 years, maybe longer. It's very, very complex. So you can't just show all details about the London Tube network to someone who's got 3 minutes to look at a map. Not even 3 minutes, right? You've got 3 seconds to look at a map and decide which platform you need to go to. So a map is such a great representation of a model. So you're stripping away all the things that might be irrelevant for that to achieve a particular goal, which in this case is actually a communication goal. Because you're communicating to travelers where they need to go or what direction they need to go in or what's possible or something like that. And the way you model a public transport network for travelers is going to be very different to the way you model the same network for engineers who are working on the heat distribution system of the tube network, right? They need to know different things about that complex system in order to achieve their goals. These are all models. We don't often call them that though. So we need to reduce complexity and focus on what matters. It's really it's an art as well, because we really need to know what people need to know about that system. So yeah, it allows us to communicate between stakeholders. So for example, if we've got some problem with the tube network and we need to ask the government for money, we need a way to communicate to the government what that problem is, and potentially a model is used to help us understand that. Who's ever, I don't know, what are you guys, like second years? If you've ever asked, I don't know, maybe you guys haven't done this, but if you're ever asking, one of the things in academic, like I has to do a lot, is ask people for money, and sometimes like a lot of money. And when you're asking someone for money, you need to communicate to them what you need and why you need it and what the problem is. And I've never put in a successful request for money that didn't contain modeling of some sort. So it might be modeling a problem, it might be modeling a system, it might be modeling a proposed system, so someone can understand and appreciate what it is that we're trying to do. It also helps us, it's even, if you've ever, we always talk about this in COMP1531, right? Especially like with linked lists. We say, if you're doing linked list programs and you're having troubles with it, what do we always tell you to do? Draw it out. So that's modeling. So we model all the time. And of course, they're great because they're way cheaper to do. So if I'm asking for $1 million to build a system, so let's say it takes about maybe $800,000 to build the system, $200,000 for overheads and marketing and stuff. Now, if it took the same amount of budget to build the model, then that's kind of silly, right? Because I need to put it in the proposal, right? So it's obviously cheaper. The other thing that's not really spoken about here is that your brains are constantly modeling. So so for example, human social behavior is very, very complex. It's incredibly complex. So what we do is model what we think about other people. So if you think about some random person, if I ask you all now to think about someone in your life that like annoys you, you'll all think of someone. But what you're actually thinking of is a simplified model of that person, because you obviously don't have all the inner workings of that person, right? So that's a complex system. It's an entire human. But you've actually built a mental model that's much simpler. And often, this is what causes lots of problems in humans' lives, because the mental models may be wrong. So you might think you understand someone and why they're annoying you, and you're completely wrong. They might just be having a bad day, but you think they hate you, right? That's because your model is incorrect. So models are often, with simplicity comes inaccuracy. A great model doesn't lose accuracy, right? But often we do. And sometimes that's fine. Other times it means, you become estranged from your family or something. I don't know. Okay. Hopefully that hasn't happened to anyone. So I think that was all the modeling in general. So let's talk about conceptual modeling. These tend to be diagrammatic representations. So for example, the map of the tube network of London. So structurally, we focus on the static representation of a system. In software engineering, we have a number of, okay, what's important, I guess let me take a quick step back. What's important for, say, a model of a tube, of the London tube? If you're let's say you're a tourist to London, what's important about the map of the network? The station names, right? Yeah, sure. That it's obvious what stations are on which line. So in that case, they use colors usually to represent the lines. But I guess you've probably built some general understanding of maps in order to understand the tube map. So there are some overarching rules for good maps that you've learnt by being a human on this planet. So for example, that we use English on the maps. I don't know. Maybe that's not a good example. What's a really obvious property of a map that if you didn't have would be really confusing? Like, what if all maps? So you get to London, you get off the plane, you go to the underground, and the map's right to left. That would just be a disaster, right? We have there are general rules. We have to have some understandings about how we represent models. So typically, it doesn't even matter if you go to Hong Kong or China or London. Maps will broadly look the same, right? Because we need common rules. And so in software engineering, we have our own set of types of models that are very useful. So objects, data, entities, relationships. So we use UML class diagrams are probably the most common. That's the is it unified or universal? Who's my fact checker? I think it's universal modeling language. So engineers got together and they said, okay, hold on, these models, what? It is unified, damn it. So these software engineers got together and they said, look, software systems are getting more complex, and I need to communicate what a software system might look like to the sales partner, to the management team. These aren't programmers. Like we need, and also, if you hire a bunch of software engineers that came from other companies, it would be kind of annoying if in Google they use a completely different way to model systems than they did to, say, Facebook, right? Because people switch. I heard the other day that who can guess the annual time an employee spends at the company Anthropic? A year? It's less than a year. It's 7 months. So turnover is very real. So we want some semblance of, just like train maps, there should be some similarities between software engineering modeling systems. And so UML is super, super common. In fact, I should get an example of the. And of course, there might be very small differences, like the colors are different, right? But the broad idea of a UML system, this is an example of a UML system, has been around since about object-oriented programming. So what, the 80s or 90s, late 80s, early 90s, mid 90s maybe? Right, so who's in OOP now, object-oriented? Anyone? No? Okay. Well, so these classes are usually represented by the yellow headers, and then the properties and the functions of a class are described in the box. And so what this is describing in a universally understood way, the different components of a software system. Now, if you think about it, let's apply those properties of a model to this UML diagram. Does it simplify code? Absolutely. So I know that there's a function called collect money in the class teller. What are we simplifying here? So what's stripped away? The actual implementation. But for the sake of a UML diagram, we don't care about that. So we're choosing what to remove from what we express in the model. Entity relationship diagrams, ER diagrams, are different There's a few different ways to represent an ER diagram, but what we're describing here is the relationship between typically properties in say a database. So what we're representing here is more the relationship between multiple entities of a system. So if you can see, I don't know how well you can see this. Oh, I don't know what's going to happen here if I click it. So this is one of the ways to represent ER diagrams. Can you see this? So what these weird, have you seen these before? They used to be actually much more important in a computer science program, but less so today, but we'll talk about it. But like these weird symbols, the two lines or the crow's feet here, represents the type of the relationship. So for example, a single course will have many classes. That's what this diagram is trying to represent. So if you think about how you store data, databases today, most databases today are relational databases in that you have these predefined relationships between the things that you're storing. So in this case, right, you can obviously kind of logic through that in a university course, there are multiple students. So you go to a university course and you read the diagram by going, well, you go that way and there's multiple students. But students also have multiple courses. You have 3 at a time, right? So do you see how this is what this model is designed to communicate? Which is different from a UML diagram, slightly. So they're really simple, common examples of structural modeling. Have you heard now everything's agile, Scrum, whatever. Back in the day, before the modern wave of software engineering, software was typically built in the waterfall model of software engineering or project management. And so modeling was actually much more important then because, have you heard these two terms before? Or not really? So today, I'll be really simple. Today, we build software very iteratively. We build things very small amounts at a time, deploy them, test them, release them, get feedback, and continue on. Very, very cyclical. It didn't used to be that way. Software engineering used to be done much more like the way you would engineer a bridge. So if you think about building a bridge, you can't really do it iteratively, okay? You can't build half the bridge and say, yeah, it's all good. By the time the cars get halfway across the bridge, that's when we'll build the second half of the bridge. But we literally do that with software all the time. When Mark Zuckerberg launched Facebook early on at Harvard, was he at Harvard? The logout button didn't do anything. Sorry, not the logout button, the delete account button didn't do anything. Because it was like, on my long list of things to do to get people using Facebook, delete account is like not at the top of the list. So he didn't wait. So if you think about that's like a support beam of the bridge missing, right? But in software, we can do these things. Like most of the time, people won't die unless you. Well, NASA just sent people to the moon a few hours ago. How exciting was that? So in software, most of our systems aren't super safety critical, and so you can do things like build the bridge as you go. So the whole reason I'm talking about this is with the waterfall model of approaching, which is still what, like, if you're building a bridge, what you do. Modeling is a lot more important because you've got to get all the details right because you've got one chance to build the bridge. Does that make sense? Because if the bridge collapses, you're absolutely screwed, right? So you want to be really careful. So that's why typical engineers do a lot more modeling than software engineers do. Because we can justify, if you're building Facebook, right? Well, this will change, I'll just fix this and then I'll add the delete account later. So the models would actually be incorrect. But like I was saying, actually, I think now that we're coming to software engineering being a lot faster with AI models, modeling is actually more important. Because if you get the model done right, then you can just ask a model an AI model, to build a system very closely to the specification. So it's also a way to specify how you want software to be built. Is this kind of obvious? Or not obvious? Is it making sense, these structural types of modeling? But they represent static overviews of a system. And I think the best way to understand that is to look at the inverse of these behavioral models or these dynamic modeling. And the dynamic modeling, to really be simple, is more about showing how a system works while it's working. A train map is a structural representation. But if you're somehow describing how people flow through the train network, that would be a behavioral or a dynamic model. And we do have these for software engineering. So it's the way we describe how data, usually data, flows through a system. And so we use state diagram and use case diagram. So if I bring up a state diagram, so here's, this is a fine example, I think. Whoops. So do you see what we're describing in this model is when a user does something like place an online order, literally what is the flow of steps that will occur in your system? And how does the data get passed around to the different components? So you can imagine, right, if you're the London Tube network, whoa, why did that click out of it? If you're the London Tube network and you've got this problem, okay, so to go from Piccadilly to Victoria Station, for some reason is taking travellers too long. Okay. So what might you do? You might produce a dynamic model of literally what do the humans going on that route need to be doing step by step so that you can find where potentially a bottleneck or some issue is. Like maybe the way that the trains time up at the commute intersection is unoptimized, and so they're waiting mid-transit for a long time. So you remove everything out that's irrelevant, right? So that you can focus on that flow of the user's behavior and understand what maybe the problem is so you can optimize it. But do you see how that's very different to a structural representation of a system? So a map is structural, a flowchart is typically, something like a flowchart is dynamic. I'm assuming there's no questions because this stuff is kind of straightforward. But not because you're, I mean, it's not the most interesting topic, to be honest, but whatever. It is useful. Yeah. So state diagrams are one of the most common types of diagrams that you can produce. They are dynamic, it's a dynamic model. So the door being opened or closed, if I want to track the state of that door and its transition states, I can describe what are the potential states of the door. And again, why is this a model? Because it's simplified. Because I'm not describing every single angle at which the door could be placed. It's either open or it's closed. I'm removing complexity so that I can understand the model. So that I could do something like write a program that says if the door is open, the noise is too loud, shut the door. But imagine if that program had to be like, if the door is 1 degree, shut the door. If the door is 2 degrees, shut the door, etc. But of course, depending on your goals, what you choose to incorporate into your potential model states is a decision. So of course the door could be locked, unlocked, and opened or closed. Or potentially a combination of all of those things. So it could be closed and locked, closed and unlocked. Probably can't be open and locked, but maybe, right? Potentially this diagram didn't sort of match over correctly, but what it's meant to be is that the locked and unlocked arrows join to that close. And so what this is describing is that, well, you can't lock or unlock a door that's open. So it's communicating a lot of information, still simplified, about a system so that you can understand it. Now, obviously, something like a door is not really something we need to model because it's simple and but it's actually because you have an internal model about doors. Actually, like there's like everything in the world is like, it's all models. Everything we do is about modeling. Like that's why LLMs are called models. So a large language model is a very complex simplification of all written data in the world. Okay, this is where it gets more interesting. So state machines are very, very interesting because actually they allow us to programmatically define complex systems in very well-defined ways. So state machines are less like a diagram or a UML or something like that, although you can define them that way. But they're used all over computer science to build various systems like regular expressions and things like that. It allows you to define a set of states or a sequence of states. So the door has two states, open and closed, for example. And you have transitions, so the door can be opened, but only if it's closed. So the transition in this case is open or closed. And you have rules. So the door has transitions like open and close. The door has states like open and closed. Unfortunately, in the sense of a door, they're both the same word. But do you get what I'm saying? A door can be open and closed, and a door can be open or closed, and it can be opened or closed. I'm getting stuck. But there are rules that define how the system can move between states. So what that simply means is that an opened door can't be opened. That would be a limitation or a rule placed on the state machine. But state machines, and there's many ways to express them, allow you to programmatically encode these rules and these states. And we use it all the time in computing. So UI screen flows, the login, logout process is a case where we really want to do state machine work because we want to capture every single possibility. So a door is a very simple system, right? It's got like two states and two operations, maybe locking and closing, but still that's very simple. But you need to make sure if you're building a login and logout authentication system, you really do need to build a state machine for that system because you need to consider every single property. So what if a user logs out and they're already logged out? You say, oh, well, that's not possible. But hold on, what would happen if someone hit the logout route via an API call and they're not logged out? Your state machine needs to cover that. Network protocols like TCP, and games are full of state machines because games are very, very complex systems. A lot of computing innovation comes from video game development. So really simply, like a character that's idle, what can an idle character do? Well, they can run or they could jump. And what if a character is running and then the character jumps? Well, that's a running jump, right? So you need to model all these states. And then if you think about how complex games are, you don't want to get in the situation where you have undefined behavior occurring. So what if you're running backwards and you jump forwards or something like that, right? You need to set what a state machine will allow a developer to do to say, well, you can only jump from these states. Otherwise, you could just jump while you're already jumping and just jump infinitely. And that's where you get these glitches. If you look at the old, Mario, Super Mario World, whatever, and they do the speed runs now, and they do these weird reverse triple back jumps to break through walls and things. It's because there's an implementation error of the state machine that drives these states and these transition triggers. And usually they're quite complex states to get into, right? Some of them are so complex, but you got to be standing at a pixel perfect position facing the sun at midnight in the game time, and then you do something and then the game breaks, right? Yeah, typically anytime you're involving money, you care about describing your system with a state machine. Why? Because the edge cases where things go wrong, you could lose your money. So this example is a parking meter. So you have the states of the parking meter, you've got to make sure lots of things. But imagine something like an ATM. You want to be almost mathematically certain that it's not possible to say withdraw more money than a user's account balance or something like that. Or equally, that you don't deduct money from a user's account and not give them the cash, for example. Yeah. So why don't we actually just do this? Why don't we model the Opal card state machine? I guess now the system's even more complex because I guess you guys still use Opal cards because you get the student discounts. Is that right? But I don't use this Opal card with a student discount. So most people, I think, use a credit card now or something. But so why don't we model the Opal card state machine? So there's the card itself and then the overall system. So maybe we can use the whiteboard here. So we can probably just do something like this. I don't know. And let's do a state diagram. I'll just get another example up. Oh, there's probably one here. Let's just do something like this. So let's do a state diagram for topping up the Opal card. You know what I might do? Do I have Figma installed? I might use Figma because I'm, I think, a bit better at it. Oh God, no, don't worry. Oh no. Be able to quit this, okay. FigJam, does this work? Okay, go away. Okay, so I got an Opal card. I want to say like add $20 is the action that's being taken. I know these might not be the right sort of like shapes or whatever, but let's just think about it. So what could the state of the Opal card be in? Let's just like think about it. So like the way I'm trying to think of this is this will flow off, for example, into multiple branches. And I don't know how many there might be. Someone want to yell? Okay, expired is a good one. Lost. Let's put it on and we'll think about it. Is there a difference between expired and cancelled? I actually don't know. Sorry?
Like, is this like a physical $20? It could be like a digital and card decline, right?
Let's say that the payment went through. So now we're describing the model of how the $20 gets placed onto the Opal card.
It could be completely normal Opal card, but just slightly in debt.
Okay, yeah, so negative balance. Whoops, what else? In positive balance. Okay, great. There's more. Okay, great. I'm going to stop doing the lines, but you get the idea. So it could be mid-journey, let's say that, yeah. Or it could be tapped off.
It could be like a bank going on so you get more dollars.
A what?
Like a coupon.
But does that apply to if you're just adding balance to the card? Probably not. That's like when you're deducting from the trip, right?
It's like a event where like if you add 20.
But is that real? Does that really happen in the Opal network?
No, baby. I'm from Australia.
Oh, I'm not from Sydney, right? So I don't know. I don't think they do that though. I don't think there's like a double Opal credit day. Is there?
You never know.
No, but we are the Opal people, right? So we should know that. Well, I mean, this is a great point where like one person might not know all the potential. Maybe there's something weird like that, right? Like, I don't know. But you'd have to go talk to everyone in the Opal system and make sure that that's not the case. But I don't think there is something like that, so let's not worry about it right now. There's one more that's in my mind that certainly would occur. Yeah, I was thinking it's a brand new Opal card. Oops.
Is it limited how much money for a Opal card?
Anything else?
You maxed out your Opal card already?
They might actually have a max. That's a great point. I imagine they do. They don't want like $10 million Opal cards, right? Maybe, you know. Anyway, so you can imagine like Opal's not even, I mean, it's actually pretty complex, but it's not the most complex system in the world. And we're just at step one. We haven't even measured what if the, okay, I guess the next thing we should probably do is cluster these. So many of these states in a state diagram will actually have no consequential implications to the system. So what I mean by that is, if a card is cancelled or expired, they're probably going to have the exact same result. So we might need to do a bit of clustering, right? And what we would say is that we can basically merge them to simplify our model, because they will always do the same thing, which might be refund the $20. Whoops. Similarly, like negative and positive balance and zero balance, they are different states, right? But systematically, they're not going to impose any difference on the system. You're still going to add the $20. Now, again, if this is the tap-on sequence, then yes, a negative balance will decline the tap-on. But for topping up, right? So this is the simplification component. We're simplifying by focusing on one slice of the system. Again, tapped on and tapped off, don't think it's going to make a difference. If it's new, I probably also won't make a difference. Yeah, I'm not actually sure about that. So maybe new actually would require some extra steps for the user to complete, like the ownership details or something on the machine. Maxed out, I imagine. So the other thing is like often, like, because if you're maxing out, then I imagine we can't put the $20 on, so you will have to refund it. But you might have to display a different message to the user. So sometimes when we describe these models, right, all of these come out and do the same thing, which is still refund, whoops, right? But we communicate that on that flow is like the warnings might be different, right? So maxed out card, rich guy here. I mean, if you got a maxed out Opal card, I'm kind of worried. You can give me some money, right? So. But that might be different to, like these might just have no message, right? So they just go straight to success. Whatever, you get the idea. So this is kind of an ugly model, but I think the trick with this type of system modeling is that you need to pick your level of detail. You can't contain all components and states of a system. Otherwise, then you're not modeling. You're you're actually just programming. Do you see the point? Because programming is also modeling, actually. You're writing code that details the instructions that should occur for what should happen between states. but it's at a level even more detailed. But because it's so detailed, it's so costly and so precise that we do simplified modeling to help us understand our systems and communicate them to other people. So why might you model? So now, you might get together over a few weeks, you design your Opal system, you make sure you cover all your edge cases, and you take your model to your technical team or some other acquisition team, and you say, given that this is our model, like what software services might we need to procure to build this? Or like, given that this is our model, how many software engineers do I need to apply to this system? So they help us make very serious and real choices. So modeling is not just some little thing that we shouldn't worry about. It's actually quite important. If you've got 100 software engineers in your company and you're a technical manager, your job is actually to assign resources. And maybe you can do modeling really well in your head because you're super experienced, but often, like maybe you encountered this just now with this very simplified example of modeling the Opal system, systems are often more complex than we imagine. We always forget things. So modeling helps us map out that complexity so you can say, oh, actually, this might need 10 software engineers full time or something like that. Cool? Do you want to take a quick break, come back? I think there's a few more slides and then we'll do something a bit more general. Okay, great, let's do that. Yeah.
Yeah, this is 1.21 last time.
We're talking 2.51 summer terms number.
Because we did it in the summer term.
Why did you both do that?
Sadism.
Sadism.
No, like, I only did it this time because Henry was taking the class.
Oh yeah. Henry's great.
Yeah, love him. But this guy's like in Poland or something, I don't know. He was in Germany.
Yeah, he went to, yeah.
I don't know if he come back. But I don't know, he's like,
He's back. He's actually in New Zealand right now. Yeah, we travel all the time. Are we back live? Okay, great. So actually, just earlier we were talking about the checksums for the credit cards. So they use something called the Lund's algorithm, which is here. Let's see, I haven't looked at this before, so let's see if we can figure this out. So if we have the account number 17893729997, which is the payload, okay, we know this. Check digits not yet included. What? Anyway. So reverse the digits, 79927398871. You do an alternative multiplier. So I guess this protects against flipping two numbers, right? That equals then 14918, okay? And then you just sum the two-digit characters, I suppose. So if you have 7 times 2 is 14, that becomes 5. You just add 1 and 4. So do you say, and then you leave the single digits. So you get 59925398851. Then you sum all of those to get 56. Then you, the check digit is equal to 10 minus the sum, mod 10 is 4. Okay, so you add 4 at the end, and you have a checksummed number.
yeah.
So so the full account number would be this, and if you did 718937, even without internet, you can apply that algorithm, and you will determine that. So you would, if you're applying the algorithm, obviously you just ignore the last digit, which would be the same. This is a very cheap algorithm, but it's designed in such a way that the simple things that humans get wrong, like swap out a number or swap two numbers, will result in a different checksum. And so you won't get the number 4 statistically, and you'll be happy. I don't know if this is the one that like actual credit cards used. I don't know if it is a single digit on most credit cards. I thought it was actually 4 digits. Sorry? The CVV is different again, I think. That's a security code, right? Actually, God knows what's happening there. But I know in the credit card digits themselves, they apply either this algorithm or one like it. Cool. Oh, the more you know. But yeah, so you can verify this checksum of a credit card. I wonder, what would be actually very fun for you should. I'm not going to do it now on this stream, but you should checksum your own credit card number. Don't go there. Yeah. Actually, the first time I was teaching this class, I shared my private SSH key to the whole stream, and I had to immediately change it. It was so stressful. Anyway, yeah, I think you could try doing this on your real credit card and see the checksum that you get. Okay. All right. So let's summarize models. Talk about one more thing I wanted to talk about with modeling. And then we can just do some general stuff, or talk about some other topics that are causing us headaches. So yeah, models, we use them every single day, whether or not we use the term model or not. You should think about the models that you have in your mind, especially about people, university, your lecturer, your friends, your family. You should be metacognitively aware that what you think about other people is only a simplified model of them. And this is how we navigate every single system in our life. And some people make models very differently to others. So what they think about themselves, that's the trick, right? I don't know, I'm not a psychologist, but what people think about themselves is also a model, right? It's like the classic thing they're realizing now is like emotions are driven by your gut bacteria and nothing else. Like we don't know that, we just think I woke up in a bad mood or something. So you're basically always dealing with models. And there's different ways to model things for different goals. Structural or dynamic are two classifications typically applied in software systems. There's mathematical models of systems. There's mechanical models of systems. If you're building a bridge, you really care about, say, the structural integrity. So you model the bridge and the weight that it can hold. If you're designing the power network of a city like Sydney, you really care about modeling because you want to simulate. We didn't actually talk about, my kind of first real job outside of, I was still doing my PhD, but I had this job, it was kind of with defense, so let's not talk about it. And we, in defense, actually, like lots of work in defense is about modeling. And the reason is that if you model, you can simulate. So you can run simplified versions of really complex systems and try out every possible permutation you can think of to see what predictable outcomes you get. This is the other. So some models aren't just like a map or a diagram, but they're actual something simplified versions of systems that you can actually run, right? That's kind of a different type of modeling than we're talking about today. But this is all modeling. It's like everything. Truly, everything is modeling. It's very interesting. Anyway. State diagrams are another very useful type of modeling. I'm actually going to show you an example now of using state diagrams. Well, and finite state machines. And the reason state diagrams and state machines are so useful as models is that you can actually program them. I'll show you examples. Yeah, if you design before coding, if you plan before coding, what is a plan? It's kind of a model of your system that you're going to build. But it helps you think about the kind of problems you might encounter when you're spending the more expensive time of designing, of implementing the system. So basically, models might sound like a boring lecture topic, and to an extent they are, because I guess there's no code involved usually, but not always. But it's actually something where if you think about the world, a great software engineer, a great programmer will think about software and engineering as models. And this is one of the things that this is why sometimes computing people or programming people or mathematicians see the world differently to others that don't have this modeling perspective. Anyway, who's used a regex before? Regular expression, yes, a regex. One of the most important components of modern software. Did everyone see the Claude code, source code got leaked 2 days ago? So the entire source code for Claude Code, the client, so not the models themselves, of course, on the back end, but the actual code that runs when you who uses Claude Code? Oh, no one. Oh, I do. It's kind of great. Yeah. Anyway, they accidentally released all the source code. It's amazing how much of the Claude Code source code is regular expressions. There's actually quite a bit in there. So who's not familiar with a regular expression? You can be honest. I was going to say we could do a quiz and we'll see how you go. So regular expression is a term, it's a pattern. Let's see, what's a great definition? Yeah, there's like very strict definitions of what makes a regular expression regular, but it's a sequence of characters that specifies a matching pattern for text. So essentially what that means is if you've got some, here's an example here. So there's a sequence, some text here, right? And the blue rectangles, can you see this? Represents matched patterns. And if you look at it, you might say, well, this doesn't really make much sense. So we have RIE, then we have RAI, then we have RE, then we have RU. So it's not like we're just matching, for example, a sequence of characters. But what's being described here is a very specific pattern to be matched. And the pattern here looks to be something like the character R followed by a sequence of vowels, where that sequence can be any length. So what a regular expression is like a language for how to describe the patterns in which you're trying to match. Have you done regex in any other courses?
Yeah, 2041 is.
Oh yeah. So take what Andrew says about regex over what I say, because he knows more. So here's the pattern that's being matched. So regex is the sequence that describes how we do this. So we're looking for the specific character R, that's the /R. The square brackets represents any character in that sequence that's in the square brackets. So any A, E, I, O, U. So any vowel. The plus represents, now you guys test me. So the plus is 0 or many?
It's 1 or more.
Damn it. And
More is an asterisk.
the asterisk is 0 or more. So that means in this pattern there has to be a vowel after an R.
Otherwise, for example, I come to
Yeah, that's all right. I should have known. Yeah, I should have implied. Otherwise, Rome. Well, I don't like. Well, why isn't Roman's pattern matched here? Yeah, it's only lowercase r. So if that was forward case, if it was bracket, square bracket R, capital R, I guess you don't need the forward slash. Then followed by.
You just tend to wrap regexes in slashes.
So that's all it is. So it's, yeah, you're right. Sorry, yeah. So it's like that. So it's just like, yep. But we know it's not just 0 vowels. Otherwise, any R on its own, I'm assuming there's one, would be matched. Or ears. Yes.
There was like a dollar sign on the output.
The dollar sign is, okay, the dollar signs are usually like a programming language will have specific characters so that it knows that what it's looking at is a regular expression and not just a different expression. So dollar signs are often used as the tail. Yeah, it's just like, yeah. But that's like an implementation thing, not an actual regex language feature. What is it? Yeah, I used to use regexa. Is that still around? Is this the same as regex 101? Oh yeah, it's similar, right? So this lets you like play with regular expressions and lets you visualize them. They are incredibly useful. They're probably all over 2041. We use them all the time. I've even written in VS Code, there's a button when you search for something to let you type in a regular expression rather than just a search term. It is super, super useful. Okay.
It's a good time to bring up that in Claude source code that have regex for like swear.
Oh yeah, all right, let's look at it. Claude code source regex swear. Are you guys gonna like report me to UNSW HR for showing you bad words? Do I have your approval to proceed? Who said no? You. Yeah. So what they've done is, so obviously you can type in any. You can type in anything to Claude Code, right? It's just like an LLM. And what they wanted to know was if someone's frustrated, it might mean that they're not happy with the previous Claude Code output. So they wanted to capture if anyone has entered in anything to the terminal that provides a signal of a negative pattern. And so what they did was, okay, let's think about what they could have done. They could have like gotten the component onto the server, run it through the model, and asked the model to determine if there's a negative pattern. Like LLMs are very good at that. But it's very, very expensive to do that. So what did they do? They said, well, screw that. Let's just we know lots of words that usually signify someone's pissed off. So let's just look for them as a regular expression. So the input that comes into Claude Code, run this regex over it. And the great things about regex is they are extraordinarily fast. Over very long periods of text. So if someone types in either WTF, WTH, FFS, OMFG, shit, either shitty or shittiest. So that could be either or. Dumbass, I should probably stop reading it. Dumbass, horrible, awful. Yeah, I'm going to stop reading it. How they get demonetized. What the hell? I'm going to skip some of them. You can read for yourself. Anyway, they test the input on the negative pattern. And if the negative pattern is true, they are actually, at the moment, we don't know what they do, but they are scoring some sort of signal. Don't take photos. I'm joking. They're keeping track of it on the back end. And actually, probably what they would eventually do, I imagine, maybe some research, maybe some experiments, but they might even apply something like RLHF on that signal. Does everyone know what RLHF is? So reinforcement learning from human feedback. So they can actually train the next version of Claude to produce fewer output, less output, like the type of output that got back the negative signal. It's very interesting stuff. But it's like, this is a great example of like a computing topic doing something quite odd. The other one is, the other famous one is like, what's the regex for checking an email is an email address? Whoa, whoa, whoa. Why is this just moving around? Okay, here. No, that's bad. What's the real? Official. There was one. There was a really great. Here it is. So like, this is a finite state machine. This is kind of what we're talking about modeling. So in order to determine whether or not an email address is an email address, you have, when you type in an email address into any form, it could be like, oh, that doesn't look like an email address. That's always regex, always. Okay, so then the question is, what is the regex for determining what an email address is? It turns out it's so complex, I don't even think this is the full one. I mean, I can't even read this, but if you look at the state machine, it's like, I mean, you get the idea here, I suppose. Turns out like you can do lots and lots of things with emails that are legal. Actually, most email regex is incorrect. So most email forms that allow emails to be input that determine, like, do you see what am I trying to say? Most email forms that validate emails do not actually correctly implement the correct email standards. Email goes back a long, long time. There's lots of weird things you can do with emails. And many of them are not correct. It turns out to do it correctly, I think that it's even true that regex is not powerful enough actually to do it. There's probably some great articles on it. But anyway, for most things, regex is very useful, even for something like an IP address. But a regular expression, if you think about it, okay, is just a model. And it's a finite state machine implementation of a model. It's an implementable model. You're taking a very complex set of possibilities, every possible email address, for example, and describing that pattern in a simplified way that's communicable and testable. So models are not just this woo-woo thing that like your product people build that you don't care about because it's a diagram and I only do code. Models are extraordinarily useful tools. So a regular expression with some caveats, because people in fact, I really suggest you do this. In 2020, I think 2023, if you go to YouTube and you search Jake Renzella, COMP1531, Rob Pike in YouTube, he was the guy that wrote the Go language. He wrote UTF-8, the standard. He wrote Plan 9, the operating system. He wrote a text editor that was part of Unix. He was at Bell Labs. I think he still lives in Sydney. He came to do a guest lecture in 1531. He has a whole spiel about how we ruined regular expressions by making them irregular, which I don't really fully understand what he was. Anyway, go and watch it. The whole talk, it's only like 40 minutes. It's really, really good. If you just Google that, you should find it. I really recommend you watch it. But he talks about regular expressions, what makes them regular expressions. But they are, as long as they are technically regular expressions, which unfortunately not all regex is regular expressions, but if it is a regular expression, they map to finite state machines. So what I mean by that, so the regex AB can be represented as a finite state machine, which is usually represented in diagrams like this. And what this diagram is, so just so you know, the regex AB means the character A followed literally by the character B. It's one of the most simple character regexes you can have, right? And this C here is not the character C, it's the complete state. That's why it's got the double rings around it. So the diagram represents a model of the capture pattern. So the character A followed by the character B. Or the character A followed by the character B. The ones in the bubbles are just the steps of the finite state machine. But that is it. No other representation can occur that matches. But if you look at something like A or B, you have the step 1, it could be A, or it could be B, and that's it. So that would be a single character. But you can see they get maybe more complicated. So now what's a curly brace in it?
So it's like the amount of repetitions?
Okay, so 2 A's, 2 or more A's, or B. 2 or more A's and followed by B. Is that, but then how does B, how does that work? Oh, I'm so sorry. Yep. So it should be A, then A, we know it has to be like that. Then there could be more A's repetitiously, definitely followed by a B. Anyway, these are models of complex systems. And they're great because you can actually program these and use them to pattern match in any size, basically any size text documents. Regex powers most of text editing, search is all regex. It's really, really useful. I really strongly, 2041, I always say take 2041. Andrew will probably motivate it better than I am, but if you understand regex really well and you know it's a tool in your arsenal, you'll be an amazing computer scientist and software engineer, or it's one part of it. But yeah, you should go watch the Rob Pike lecture. In fact, if we end a bit early today, you could actually just watch it. But he talks about how regular expressions there was like a feature added to regular expressions that made them irregular mathematically. Regular is a term for mathematics. And actually, unfortunately, that's what causes regex to not always be fast. But that's why he's saying here that irregular expressions are not finite state machines. But we're getting a bit outside of my understanding here. There's a bit of mathematics here. Anyway, I just thought I would talk about that. That kind of concludes what I had prepared for today. We got through Tuesday faster than I had planned. Is there anything you guys wanted to talk about, discuss, ask? Otherwise, then what I would suggest is in the 25 minutes that you have, go and watch the lecture he gave.
Couldn't find it.
You couldn't find it? It's that one. Yeah, I didn't really advertise it super well. But yeah, it was a really great lecture. I should ask him if he's around to maybe do another one. But sorry? Yeah, it was in a different lecture theatre. Is that okay? It was in the science theatre. Yeah. No questions online or in the room? There's nothing you guys want to talk about? Okay, shall we call it? I'll give you back 25 minutes. Go watch the lecture. Oh, you have another lecture afterwards, but you can watch it on your phone. Okay, thanks everyone. Next week is my last week with you actually, and then it's back to Shaveen, but I think there's only like 1 or 2 more weeks after that. So, all right, good luck with the assignment. No? Yeah, I know. All right, thanks, Liam. Let's end the stream.